Hi everybody, welcome back to the Talos series. I'm beginning now with the integration tests. That's the Talos cube or the Borg cube, whatever you want to consider it. I'm testing now each instruction of the instruction set. I have Talos connected via serial port here to my PC. On the PC, I have here the instruction set, and you can see the instructions from opcode 0, which is a no-op, all the way down all the 256 opcodes, including the jumps, including this. And then we have some other pseudo instructions which have the same opcodes. Remember that in Talos, the opcode contains the operands. So 256 opcodes doesn't mean 256 different operations. It means 256 different combinations of operation and operands. And here I have a Terra terminal window connected to Talos. Here is how I interact with Talos. The system, as you've seen before, has the motherboard with its chips in there, hidden in the middle. And then we have the control card of the CPU. This is the addressing logic card. This is the ALU. And on the other side, let me see if I can shoot it for you. Here we have the register file card. But to see what's going on, the ALU is sufficient because the 4 registers are passed through to the ALU always. So we can see their contents on these 4 LED bars in here. So I don't need to film from the back. The ALU will give us the information we need. This will be a difficult video to make because it needs to be handheld. There are just too many angles to shoot from. And I also need to use my hands to type stuff. And it probably be a little bit chaotic, but I wanted to give you an idea of what I'm doing because testing this whole thing takes a while. I didn't want to leave you without any update all this time. I wanted to give you an idea of what's happening, what I'm doing in the background. So here's what I would be doing. I'll show you a few examples of the testing. We have now a few different operations implemented in the BIOS. There is a BIOS update in the repository right now. Some of them control the status of the CPU. For instance, I now have the halt on and off operation. I can do halt off to unhalt the CPU. These LEDs here indicate the reset, halt, and clock status. So right now, halt and reset are off. They are active low. This means that the CPU is in reset and being halted. So if I now do a halt off and execute it, then the halt LED is now burning, meaning the CPU is no longer halted, but it's still in reset. So I just go and do a reset off. And now it's halt and reset off. And if at this point I just play enter, I just press enter without anything on the command line, then the CPU will do a clock transition. This first LED here shows the status of the clock line. So now it's low. If I press enter, I will just press enter here. The clock will go high. If I press enter again, it will go low, high, low, high, low, high, low, and so on and so forth. And of course, other stuff is happening because I'm now clocking the CPU by hand. Instead of using the oscillator, I'm clocking it by hand so I can follow every step in order to test everything. So let's put the CPU back in reset because I need the CPU to be in reset to take control of the memories. So reset is now on. And you see that this LED bar here is now all pulled up. This is the output of the instruction memory. When the CPU is reset, the bus that goes to the instruction memory is tri-stated. So you have the pull-up resistors setting the state of this bar. And now you see that it's unhalted but not reset. The reset LED is off and reset is active low. So the CPU is in reset, and that means I have control of the memories. For instance, I can do an instruction memory peek at address 000, and there I have opcode x0, which is a NOP. This is the hexadecimal value of the opcode over here, and if it's 0, that's a no op. So we can test instructions by just poking the opcode in the instruction memory. So I can come here and do ipoke at address 0000, and I'm going to put opcode, let's choose one, let's take the first one, opcode 1, which is A high receives the immediate value. So let's put 01. Then we can peek again just to make sure that it's there. I'm not going to repeat this peek all the time, but just to give you an idea of the process. So now we have a 1 there. And because this is a immediate operation, the immediate value should be in the next address of the instruction memory. So we have to poke that too. Let's poke in address 0001. And then we poke, let's do 55 because it's an alternation between 1s and 0s, so it's very easy to see if the bit order is correct. So let's poke that in there, and then we peek that to make sure it's correct. I would just trust the ipokes later on, but just to give an idea now. Oh, syntax error is not implemented yet. I pick 001, and that's the 55. So we are good to test it now. If I take the CPU out of reset, doing reset off. So now we see that because the program counter is pointing at address 0 of the instruction memory, what it's seeing there is a 1, which is what we just poked in there, that 1. And that value has to be transferred to the instruction register. To do that, I have to clock it by pressing enter. It's 2 presses of enter per clock cycle. So it will probably take 3 presses now because the machine is starting from nothing. So there we have it. The opcode 1 is now in the instruction register. It's also in the immediate register, but it's ignored there. So it's the instruction register. If I type it, if I clock it a couple of times more clock transitions, then this value will address the decoding memories. And here we should have the decoded instruction word corresponding to this opcode. So let's do that. Now we have it, and these are the decoded values. That's an immediate register output enable, and the immediate, which came from instruction memory, is now in the immediate register. That's the 55 in X. It's a 1010101. That's the 55 that I poked in address 1 of memory. So this is in there now, and now we have the decoded instruction word here, and it's supposed to load a value, as we saw here, in A high, register A high. So it's supposed to put the X55 in address A high. And where is A high? We can see A high here. There is a spurious value there now, but when I press enter, it should latch the 55. So I'll press enter now. There we go. That's the 55 latched in A high. And I can do this for every single instruction. Some instructions actually require other instructions to set the value of certain registers correctly. But let me give you another example. Now let's take instruction 7, which is address register 1 increment. So what we do, I will put the CPU in reset again so I can access the memory. And now I'm going to poke in address 0 the operand 7. So I'm going to poke a 7 in there. And now it doesn't matter what is in address 1 because this doesn't require an immediate. So I take the machine out of reset. And now we see that the 7 is already at the output of the instruction memory, but not latched in the instruction register yet. So I'm going to press enter to clock the machine. Now it's latched. It's also latched in the immediate register, but it's ignored in there. So now it's going through the decoding process, and if I clock it a little more, I have the decoded instruction, and this is just the count enable for address register 1. It's indeed only one signal, and if you look here in the addressing logic card, this is the address register 1, it's at 0. When I clock it, it should count, so it should go to 1. And these are the control signals involved. This is the reset, which is high or inactive, and one of these is the count enable. This one is the count enable. So if I press enter now, we should see AR1 counting to 1. And that's exactly what happens. And the program counter has counted to 2 because it's going to fetch the next instruction, which in this case is a spurious instruction because I didn't program it for the rest. It gets a little bit more complicated when we need to set a register, or maybe I can show you this first. Before it gets more complicated, let me show you this first, which is an instruction with 2 operations in parallel. Here I am I'm addressing the data memory according to the address present in the address register 1, which will be 0 because I'm going to reset the system. So that content of data memory should be loaded in a high, and in parallel, address register 2 should count. So let's see if we can do this. So we put the system in reset again so we can access the memory. Then we poke in instruction memory address 0. We poke this opcode here, X15. X15. That's what we poke in there. So we do X15, reset off. So now the X15 is coming out of the instruction memory. When I clock it, it's loaded in the instruction register. Now it's being decoded. When I clock it further, now we have the decoded instruction word. And here we have bits to activate the count enable of address register 2, which is supposed to count. And we have the control bits that will do a read on the external data memory. And the load enable of the respective register and whatever bus control we need. So all the control bits are here. Now, I forgot to poke something in data memory, so we can check if this works. So let me put this in reset again, because there should be something in the data memory at address 0, because that's what will be read to be put on the register. Let's see what is in there right now. It's a 0. So let's make it more interesting. Let's do a deep poke in address 0. Let's put let's put F0. So one nibble. The higher nibble is 1 and the lower nibble is 0. Let's make sure that it's in there. Yeah, it's in there. So now we can do this whole thing again, reset off. So now let's start again. The instructions coming out of instruction memory. Now it's latched. Now it's decoded. So 2 things should happen now. AR2 should increment. So this should go to 1. And A high, which is this, should receive the contents of address 0 in data memory, which has only the highest nibble enabled. So let me press enter now. Let's see if that will happen correctly. There we go. So the high nibble is now there, and address register 2 has counted. It has incremented. So this instruction, opcode 15, AH equals the content of data memory pointed to by AR1 plus AR2 increment. This is working. This is working just fine. So now let's do a reset on. Oops. Reset on. So the system goes into reset again. And these are the internal buses, high and low. And when the system goes into reset, nobody is asserting a value on the bus, so we just get the pull-ups. That's why it's all ones. The buses are just being pulled up. So let's get a more complicated operation now that requires more than one instruction to implement. Let's take here opcode 45 or 2D in X, this here. So it will put in data memory in the address pointed to by address register 1 the contents of register A high, and it will increment AR2 at the same time. So what is in A high? Let's look at what is in A high right now. That's the high nibble, that's F0. So this should go to data memory in the address pointed to by AR1, which right now is 0, but we can increment AR1 first. So let's first do this instruction here, AR1++, to increment AR1. So let's do an ipoke to instruction memory at address 0. We put this opcode here, that's opcode 7. We poke a 7 in there. And then in the next instruction at address 001, the next instruction will then be this one here, which will take the address in AR1, which will be 1 because it will have been incremented by the previous instruction. It will take the contents of the data memory at address 1 and put, oh no, that's not the one I wanted. Let me do this one. Let me do this one first, because I want to write to data memory instead of reading from it. I want to put the contents of A high in data memory in the address pointed to by AR1. And AR1 will be 1 because the previous instruction was this one, which is an AR1++. So it go from 0 to 1. And then in address 1 of the data memory, we will put the high nibble, which is in the register A high, as we just saw. A high has the high nibble. So after we increment AR1, let's put this opcode here, opcode 21 in X. Let's poke a 21 in there. And let's clear the data memory data memory at address 1 to make sure that we did write something meaningful there. So in address 1 we put a 0. And let's make sure it is a 0. It is a 0. So there is a 0 in the data memory address 1 right now. At the end of this, we should have F0 in there, if the whole thing will work. So reset off. So now we have opcode X7, which is the AR1 plus. Just to make sure that this will be correct, let me poke a 0 to the instruction memory at addresses 2 and 3, just to make sure that there are no ops following the instructions we are executing, because if I press the enter key one too many times and I clock it too much, I will execute some garble that might be in instruction memory and distort the results. So let's just make sure everything is correct. So at address 0 should have 7. At address 1 we should have X21. Yeah. And at addresses 2 and 3 we should have 0, which is a no op. Three, also 0. And in address 1 in data memory we should have a 0, and that 0 will be overwritten when these two instructions are executed. Yeah, everything is looking fine. So reset off. So now we have opcode 7, which is the AR1++. Now it's latched in the instruction register. Now it's decoded. The next clock cycle, AR1, will go to 1 because it will count. There we go. AR1 is 1. This is AR2. This is AR1. It's now 1. And here we should have the next instruction, which is the one that does the memory operation. It's now decoded. If I press it once again, now it's executed. And now we should see if we have F0 in address 1 of data memory. So we put the CPU in reset and we poke address 1, which before was 0. Now it should be F0. Oh no, it should be a deep peak. What have I done? Ah, you bloody idiot. Have to do this again, because now there is garbage there. Off. Okay, let's do this again. That's the AR2 or AR1. That's the AR1 ++ that has been executed. Now that's the memory operation. It's decoded. And now it's executed. Okay, let's do this right now. So reset on. And now the peak on data memory at address 1, which was 0, now should be F0. And there it is, F0. So this is what I'm doing for each of the 256 opcodes, which in fact are a combination of opcode and operands, all encoded in 8 bits, because this is an 8-bit architecture. Maybe I'll show you one more example, maybe with an ALU operation. Let me see, what can we do here? Yeah, this is trivial. Just an ALU operation is pretty trivial. If we look at the addresses now, only A high has something. If I put something in the other registers, we can do a meaningful ALU operation. But now we have to write a little program first. So let's do I poke 0, 0, 1. No, 0, 0. We don't need to poke to A high because there is something there already. We have to poke to A low, B high, and B low. So let's do in address 0, 0, 0. We do this one here, and A low receives immediate. That's opcode 2. And then after that, we need the actual immediate. Let's do that immediate as 55. Oops, and then we need in address 2. So this is a little program already before we even have a proper machine monitor, just using peeks and pokes. Then we do operation X3, which will load an immediate on B high. So this should be opcode 3. And then we need the actual immediate value that we are going to put in that register. So let's do the low nibble now. Just put something different. And then the final opcode in address 4. We will do the opposite. Oh no, now we need the opcode 4, which is this one here. We will load BL. So we already have A high, now we will load A low, B high, and B low. So that's the opcode to load B low, and now the actual immediate value that we'll put in that register, that goes in address 5, and then we do F0. And now every register will have a different value. And then after we do all this, now we do a full add. Let's do A plus B 16-bit. Let's do the 16-bit add, which I actually haven't tested yet. That's opcode 86. So we will put in address 6 of instruction memory. We will put operation 86. Let's see if this will work fine. We take the system out of reset off. So now the first opcode will come in, opcode 2. After that, we have the first immediate. It's all being loaded. Then opcode 3. Then the next immediate, which is the low nibble, or 0f. That goes to the immediate. Everything is decoded here. When I press enter now that register will contain that immediate. And now opcode 4, which is loaded in the instruction register. Then there comes the high nibble, which is loaded in the immediate register. Everything is decoded. And when I press enter, this is now in the register. So the registers now should all have values. There they are. This was already there. This we just loaded, this two, and this we just loaded. And you can see the same values, of course, in the register file card. But because they are here as well in the ALU card, it's easier to see. And then, if I press enter once again, that's the ALU operation proper, which goes decoded there. And this is the result register. So A is this and this. This is A high and A low, B high and B low. Adding them as 16-bit values gets you this. If I press enter once again, now we are out of it. Sorry, the previous value was the correct one. So this is working. So we just executed a little program now in this thing. So this is it. I just wanted to give you an idea of what I'm doing. I'm testing each instruction individually. Sometimes I need to write a little program, just like you saw me right now, to test an instruction that needs certain values in the registers for it to be meaningfully tested. I needed to add instructions that fill those registers or fill those memory locations with some values. But other than that, it's an individual test, instruction by instruction. And after I'm done with this, then I have to do more sophisticated tests, like is the halting working correctly? Because there is an entire protocol to halt the CPU. It cannot just be halted on a dime. I have to test that. I have to test more of the memory operations. We tested one together right now, but I want to test more complex ones. And then test the control logic, the conditional jump operations, individually and as part of some more meaningful programs as well. And I have to improve the firmware. So instead of just picking and poking with opcode values, I can actually write the mnemonic, and the firmware can translate that into the actual opcode value. That's much more intuitive, and I want to add other operations in the BIOS, like listing the code that is in memory instead of picking one address location each time. But we are in the final stretch. I mean, the basics pretty much work. Via the serial port, I have full control of the machine. All the initial instructions, they are all working. So there is no dramatic error here. There may be errors in the details. Yeah, but at least now you know what I've been doing in late night hours almost every day, going through the tiring process of testing instruction by instruction. But it's also rewarding, especially when they are all working. When they are all working, it's a lot of fun. And so far, they have all worked. And just to anticipate something I plan to announce more formally later, this build is a very expensive build. I'll donate one to the museum here because, you know, with a slow clock, like 10 hertz, you can see these LEDs flowing, and it's a great demonstration piece, very didactical. I think universities might want to have one, not one per student, but one per class. But this is between 1,000 and 2,000 euro build. It's expensive, lots of boards, lots of parts. I will build a Talos CR, Talos cost reduced, which I hope will be smaller than a single card here, or maybe as big as a single card, because this is a standard ATX format, micro ATX or mini ATX, mini ITX, I think this is the format. So I'll put everything SMD, no LEDs, I'll make it as low cost as possible, and that's the version I will send to my collaborators, developers, who can write then a proper cross-assembler, maybe a compiler, an emulator, and so forth. I cannot afford sending a 2,000 euro build to a number of people. I can afford a couple, one for myself, a couple for museums, but to developers, it's too expensive. So there will be Talos CR, and both will be open source. So this is it from me for now. I'll update you once I have more to tell. In the meantime, take care. See you next time.